see. I need to make a new notebook for this class, so let's do that. So new notebook, and this will be MAT112. And mute myself because I don't want to hear my own stupid voice. Okay, so all right, so last time we did some, why am I, sorry, mute, okay. Last time we did some review on u-substitution just to kind of remind ourselves how that worked. And so what I want to do today is I'm going to pull up and we'll put this file on Canvas. We'll do this with all of the sort of things that we're working on. Oops, would help if I look in the correct place. Some spicier u-substitutions. And what I mean by that is that they're not necessarily obvious the way that they work. So let's look at what maybe is a good example to start with. Okay, so if the exponent weren't there, we'd be in business, right? We could just distribute everything and that'd be the end of it. If the exponent were on the x rather than the whole parentheses terms, same deal, right? We'd be set. We could just do it. But we can't distribute the first term x into the parenthesis term because of that exponent. Okay, so we're sort of hosed. So what do we do instead? Well, wouldn't it be nice if the exponent wasn't on the term that had the plus? Be great, right? Now we can't just move an exponent magically, right? I mean, we could, but it would not be math. So what are we going to do instead? Well, so here's where we're going to be a little sneaky. Let's let u equal x plus 1. I mean, what else do we have, right? That's the only thing that we could possibly do here. And that's fine. What's du? Dx plus nothing, right? Because it's a differential, not the integral. Okay, so great. So this integral would be x times u to the 7/2 times du. Oops, let me make that look nicer. Those of you guys on Twitch, looks like we got 5 of you. Hopefully the audio is coming through good. You guys can see all right. All right, so dx became du because they were the same thing. X plus 1 was what I chose to call u, so now I've got u to the 7/2. And I've got that x that was out there in the front of this from the beginning. Well, so it looks like we're in trouble because what should happen after you do a substitution? You only have u, right? You get rid of all of the x variables and switch them in terms of u or whatever other letter you pick. But here I still got an x left over. So you might think that we're in trouble, but what could I do instead? Well, if u is equal to x plus 1, what's x? Ah, and then I'm going to take that and substitute him in here. Okay, so this is what I like to call a flippy-flop substitution because essentially what we've done is exactly what I almost said that we can't, right? We've sort of magically moved the exponent to the other term. Maybe a better way to put it is that we've exchanged a sum in one term for a difference in the other. Okay, but now what can I do? Yeah, now I can distribute. So let's do it. All right, and so I'll have u to the 9 halves minus u to the 7 halves. Oops, that's the worst parenthesis ever. Okay, great. Now what? Well, now it's just the power rule, right? So we'll have what? 2/11ths u to the 11 halves minus, sorry, yeah, minus 2/9 u to the 9 halves. And then, of course, our glorious plus c. Okay. Is that part all right? Yeah. And then what's the last step? Obviously, we need to, yeah, just, yeah, exactly. So what was u? It was x plus 1. So just replace. So we'd have 2/11ths x plus 1 to the 11 halves minus 2/9 x plus 1 to the 9 halves plus c. Okay, so the key here was that observation, right? Is that what you're doing when you make a u-substitution is you're defining u to be some sort of function of x. Well, depending on what kind of function it is, it might be solvable the other way, right? It might be an invertible function. And in this case, when the function is linear, that's most certainly invertible, okay? So yeah. So like I said, this is what I like to call sort of a flip-flop substitution because of that sort of trick. And once you've seen it, it's kind of like, oh, yeah, like the invention of the Post-it note. Right? You see a Post-it note. Did I use this joke last semester? The Post-it. Okay. Yeah. Yeah. So anyway, okay. Does that make sense? Any questions? Preguntas and/or fragens? No. Okay. All right. So let's move on to another one that's kind of spicy, and let's see. Oops. See what you guys think you can do here. So let's say that we had x plus 3, x minus 1 to the 5th dx. Okay, now there are actually two different ways to do this one. Could we expand this all out, theoretically? Yeah, I mean, it's to the 5th power, and then there's this other thing, right? So we could do it. It would just take a few minutes. And you could probably do it relatively quickly if you remember your binomial coefficients from Pascal's triangle. But there's a better way, okay? And in particular, suppose that 5, the exponent, were something other than a positive integer, right? If it were anything else, then we could not do expand it all out. Okay, so yeah, so what do you guys think would be the brilliant move here? Yes? All right. Now, why'd you pick that as opposed to x plus 3, which is clearly another term there? Right. That's the one that we want to deal with, not the other one. Okay. The other one has no exponent, or it's to the first, so it's not really an issue. Okay. And then, like before, du is just dx because the relationship between u and x was linear. And then x is equal to u plus 1. Which when we come over to the integral, what are we going to get? Well, we've got u to the fifth du, and then just to spice this up a little bit more, right? So we're starting to get into like the mango habanero territory instead of the just jam and jalapeno territory. You guys know what those are? They're wing flavors at B-dubs, right? Wing sauces. The mango habanero is you got the sweet from the mango and the burn from the habanero, and yeah, it's it's painful, but it's tasty. Um, I really like spicy food. If you guys didn't guess, but the hottest I've ever had was the ghost pepper wings at B Dubs. They were so spicy I started hallucinating. Um, yeah, well, like it wasn't like a Hunter S. Thompson like full on LSD, but it was just very mild augmented state of consciousness. It wasn't like a full on trip, but yeah. Um, all right, so what's x plus 3 become? Yeah, right? U plus 4. Okay. And now that we've got it in this form, like before, we can now um, uh, distribute everything to be u to the sixth plus 4u to the fifth, and then just integrate like usual. And then substitute u back in and maybe simplify the 4/6 to 2/3. Okay, so does that kind of make sense, right? It's sort of a sneaky reverse on a u substitution, and it's not the only sneaky substitution we'll look at. It's not too sneaky, but yeah. I think actually as a task, one of the tasks you can choose to do would be to learn about what a mathematician called Weierstrass called the world's sneakiest substitution. Um, or sorry, not Weierstrass. It's the called a Weierstrass substitution, but the mathematician who said it's the world's sneakiest was Michael Spivak, who wrote a calculus book. Over your nose too. Yeah, there you go. The number of people I saw at Walmart this weekend without masks was there was one guy that was like holding it in his hand while he was shopping. It's like, dude, they don't work that way. All right. So, good. Now, this trick can be used in other situations where you might think that all hope is lost. So let's look at this. There are actually two ways we could do this problem. So the previous problems, right, the whole issue was that we wanted to distribute, but we couldn't. Well, what does it mean to distribute in a situation like this? Doesn't. Okay. But could we break this up so that it was maybe 2 or 3 terms that we could integrate individually? Well, I could write it as x over 2x plus 3 and 5 over 2x plus 3. Okay, that doesn't really help, but what else could I do here to maybe simplify this a little bit or expand it? Hmm? Okay, yeah, I could multiply by some sort of disguised form of 1 to kind of simplify things. Um, Another idea is let's do some polynomial long division, shall we? Okay, so it's probably been a while since you guys have had to do this, um, because I think I first learned polynomial long division in algebra 2 in high school, right? So it maybe it's been a few years for all of you guys, but do you remember how to do this? Well, here's the good news. How do you do long division with numbers, right? Well, guess what the algorithm is for polynomials? The exact same thing. The only difference is that we have to be careful. So in numerical division, right, if I were to do something like 1832 divided by 42 or whatever, right, when I write 1832, the place value determine the 1 or the 8 or whatever, right? The digit and its position determines its value, not just its the digit. Whereas with polynomials, there is no standardized way to write them. Okay, so what would be the logical way to do it would be just decreasing powers, kind of like we do with numbers, but you don't have to. So that's the only one wrinkle, is that you have to be a little bit more careful with your bookkeeping. All right, so how many times does 2x go into x? Well, there's two ways to answer that. 0 is one answer. It doesn't, but what's the real answer? Yes? Yeah, it's a half. Okay, because what I'm really asking is, what do I need to multiply 2x by to get x? Right? Okay, so if I, multiply over, then I'm going to get x plus 3 halves, and then I subtract. The x's cancel, that's good. And then 5 I can think of as 10 halves minus 3 halves is 7 halves. Okay, and so now I can write the original fraction as 1/2 plus 7 halves over 2x plus 3. Okay, so notice the form here. I've got the quotient, I've got the remainder, and then I've got the divisor. Okay, so now how would I integrate this thing? Well, I can take it into pieces, right? So the integral is going to be 1/2 x plus 7/4 natural log of 2x plus 3 plus c. Okay, why 7/4 and not 7 halves? Yeah, so the denominator there, 2x plus 3, I just did a sort of simple u substitution in my head of u equals 2x plus 3, du equals 2 dx, and therefore I get an extra factor of a half that's going to pop out, and so I get that. Okay, so that certainly worked, right? Okay, how do you guys feel about polynomial long division? I mean, that wasn't very long as far as long division goes, but right, yeah, okay, good, that works. All right, but what would be another way that we could have done this? Yeah. Oh, okay. Yes, that is true. We could have done a partial fraction decomposition. Um, but actually, you're looking at the partial fraction decomposition, right? And because the denominator here is a monomial, right? The first thing we would do is long division, and then we would do the partial fraction decomposition on that part, the remainder over the divisor. But since this is a single linear term, there's nothing to do. It's already done. Okay. Now, if this thing factored into like let's say it was a quadratic or something, then bingo, yeah, we could totally do that. But here it actually is not necessary. It already is a partial fraction. Now, what are partial fraction decompositions? We'll talk about that later. Um, Believe me, that'll be we'll have that fun later. Okay, so yeah, that would be an approach, and we'll see plenty of examples like that later. What would be another approach? Kind of thinking about the two evil examples we did earlier. Like, how could I do this with just a u substitution? None of this fancy schmancy algebra. Yes. Okay. Don't have to yet. Well, okay, let me rephrase the question. If I say, thou shalt use a u-substitution, what are our options for what u is?
Either x plus 5 or 2x plus 3.
There's not a whole lot of other choice, right? It's either going to be x plus 5 or 2x plus 3, right? What else do we have? Now, where is the problem here? So, okay, let me maybe rephrase. If there's a sum in a numerator, is that a problem? No, because we can break the fraction up into two pieces. If there's a sum or difference in the denominator, can you break that up? No. Okay, so what would be really nice is if I could write that as x plus 5 over 2x plus x plus 5 over 3, but fractions don't work that way, right? So, so the problem is the denominator, okay? So what should we probably make u? Let's make it the denominator, because then we can sweep the problem under the rug. Yeah? All right, so let's try that. Okay, so let's try. Let me just copy the problem back down. Let's try u equals 2x plus 3. Okay, and so what is x going to be in this when we solve? Won't be quite as nice, but c'est la vie. I'm sorry? U minus 3. And then, of course, divided by 2. Right? Good? Okay, and so then x plus, well, let's go ahead and simplify this a little bit. Let's write it as this. So then here, if that's x, what's x plus 5? Right, so that's the numerator. And then what's the denominator? Just u, okay? And then du. Oh, yeah, thank you. There we go. Because of the 2 right here. Okay, so just substituted everything in, right? Now, look what I've done, right? I've sort of moved any of the sum and difference stuff from the denominator up purely to the numerator, which means now we can break the fraction up. And we can break it up as, well, let's see what we've got. Let's see, so it'd be what? U halves minus 3 halves plus, so that's 10 halves, so minus 7 halves, all over 2u du. So we can pull the quarter out, and then we just have u minus 7 over u du. Where? Oh, sorry, so it's plus. Plus, minus, Okay. All right, so am I good now? Plus, not minus there? Yeah. Okay, now break up the fraction as 1 plus 7 over u du. Okay, and then when we integrate, what are we going to get? Well, we'll get u over 4 from the first term, okay, plus 7/4 natural log of u plus c. Good? Okay, now, of course, we're not finished, but I'll let you guys pause for a moment and scribble that down. Let me clean up my handwriting here. That's a 4. Let's make this look nicer. U over, what was it, 4? And then it's a 4. Okay. Good? Okay, so then the last thing we need to do is convert everything back in terms of the original variable, and then let's compare it to our previous answer to make sure we didn't screw anything up. Okay, so u was what, 2x plus 3? And then 7/4 natural log of 2x plus 3 plus c. Okay, let's compare that to what we had a minute ago. Okay, so that would be this and that, are two versions of the answer. Are those the same thing? They don't look quite the same, do they? Is the logarithm part the same? Yes. Okay, good. That's probably the meat here. But the 1/2 x looks different. Do we have a 1/2 x on the bottom version? Well, yeah, because we got 2x over 4, right? But if I split that beginning fraction, the 2x plus 3 over 4, so split that into 2x over 4 plus 3/4. Where's the 3/4 in the previous answer? Yeah? Yeah, it's sort of hidden in the plus c. Okay, so those two answers are the same, and this is something that maybe we're a little loose about mathematically, but the plus c in one answer is not necessarily the exact same plus c in the other answer, even though we use the same letter for it. Okay, so these two things don't look identical, but they're equivalent because of the plus c's, right? Okay, good. Yeah, so sometimes you have to be a little crafty and use the plus c to your advantage. Yeah. Okay, so questions about this one, either method. Okay, so we did polynomial long division, and we'll return to that because it'll be useful when we do talk more about the partial fraction decomposition. Uh, and when you say partial fraction decomposition, it sounds kind of fancy. It's essentially just common denominators in reverse, right? So take a big nasty fraction and break it up into a bunch of little pieces, and then hopefully you can deal with each piece in a relatively simple way. And it turns out that works really nicely because polynomials behave a lot like numbers in that they factor nicely. And yeah, so we'll get to talk about that in a bit. Okay, now Ethan, you suggested one other thing, right? Which is multiplied by some sort of disguised form of 1. What could have that disguised form of 1 been? And do what now? Okay, so negative 2x plus 3 or negative the entire quantity? Okay, so let's see if 2x minus 3. Okay, well, let's see what would happen if we did that. Okay, so let's come over here and let's say x plus 5 over 2x plus 3. So your suggestion is to multiply by something like that. So why'd you pick minus 3? Are you kind of thinking sort of conjugate-y? Okay. So, okay, so let's multiply all this out. Okay, what are we going to get in the numerator? Okay. Now what? I mean, it kind of looks like we made the situation worse, right? And in particular, the like, I mean, if we tried to factor everything, we'd get right back to where we started. Okay. We could do polynomial at long division at this point, but if we could do it here, why wouldn't we have just done it in the beginning? Okay. So it doesn't look like that's really going to help. I mean, it's true that those things are equal, but didn't help. Okay. Yeah, oh well, that happens. Let's look at a place where multiplying by a disguised form of 1 actually does work. Okay. What's the integral of secant? What's the trap answer here? Or there are several trap answers. Oh, sorry. Yes, Mr. Trap is sitting here. All answers are trap with the extra P. Huh? Well, I'm not going to say that live on the internet, but yeah. Yeah, so what's the trap answer here? Or a trap answer? Okay, tangent or secant tangent, because that's the derivative, right? Or secant squared over 2, right? Just treat it like it were an x. Can't do that. So we're kind of hosed. Now, this one, what I'm going to do, so let me scoot the dx over. So I'm going to multiply by a disguised form of 1. Does anybody happen to remember seeing this before? Ethan, I know you did, because the guy you had for calculus was both incompetent and thorough. Yeah. You happen to remember? No? Okay, it's all right. We will use some trig identities. So the disguised form of 1 will involve trig functions. Okay. And then we'll use some identities. John, do you happen to remember the magic trick here? No? That's okay. Anybody? No? Okay, good. No? All right, let's try. Okay, if I locked you into a room and said you can't come out and you don't get any food until you figure this out, you would eventually come up with this. Okay. But when you look at it, you're like, where the heck did that come from? Now, once we finish the problem, you're going to look at it and be like, oh, of course, right? In the same way that if you looked at a Post-it note and you're like, okay, a little sticky tape plus a piece of paper, any moron could have come up with that idea. But it's only after the fact that it's obvious, right? Beforehand, it's, yeah. Okay, that may not look like it's going to help at all. Let's multiply everything out and see what we get. All right, so what happens if I multiply everything out? I get secant squared plus secant tangent over, okay, now Mr. Trap just said, oh, okay, and so I get to use a little used metaphor. SOCAF, his eyes uncovered. No, do you guys get that reference? This one's really obscure.
Would you tell us?
I will, but I'm hoping that somebody can tell me what it is. But no. It's from season 5 of Star Trek The Next Generation, the episode called Darmok. Noted? Yeah. Yeah. Season 5 had a bunch of really good ones. It also had The Inner Light, which is, yeah. You guys have an assignment this weekend to watch some Star Trek. Okay, so that doesn't look like it's helped at all, but SoCath has eyes uncovered. Um, what could we do? Mr. Trapp, what do you notice? And Farden, yes, we could do integration by parts, except we haven't done that yet. So we'll talk about integration by parts next time. But yeah, that would work. Hmm? What do you notice about the relationship between the numerator and the denominator? Well, what's the derivative of the denominator? Okay, so what's the derivative of secant x? Secant x tangent x. What's the derivative of tangent? Bam! Look at that. So the derivative of the denominator is precisely the numerator. They're just written in opposite order. Okay, but it's plus, so who cares? Yeah? So what that means is that this is actually that simple. Oh, it didn't update. Yes, you're right. Okay, so why is that? Um, good question. Is this still powered? All right, hang on, guys. Let me see what the issue is. There it goes. Okay. All right, sorry about that. Technical difficulties. Okay, great. So, yeah, sorry. I was wondering why you guys were looking confused. So, yes, let u equal secant x plus tangent x. That's the denominator. And then it just so happens that its derivative is precisely everything in the numerator, just written in backwards order. Okay, and so that means that as nasty as this thing looks, it's really just du divided by u. Okay, well, once we've got du over u, then what?
Just do it.
Well, yeah, but then it's logarithm and blues. Ba-dum-da-da-da-da. Okay, so it's just natural log. And so we just get that, natural log of secant plus tangent. Okay, good? All right, so now let me stretch y'all's brains a little bit and put you to work. We just did the integral of secant. I want you guys to do the integral of cosecant. Okay, now they should work similar, right? Because secant, cosecant, tangent, cotangent, right? They're all kind of related to each other. This one has a very slight wrinkle. So see if you can try this for a few minutes, see what you come up with. And we'll see if the Twitch peanut gallery has anything to add. Coy and Farden, how are you guys doing this morning? Well, it's morning for us. It's not for you. It's Coy, I think you said you're 12 hours time difference, so it's getting close to bedtime. And Farden's in Malaysia, which I think was, what, 9 hours time difference? Something like that. And Cole, I don't remember where you said you're from, but you're probably on Eastern or maybe Central time. And who knows, maybe Dr. Dunaway came to class today. He just woke up at 4 p.m. Yeah, that's not good. I need to like set up Jeopardy music for when I do things like this. Yeah, that's true. Oh, Cole, yeah, you're not far, and you're just in. He's all the way in Peru, Indiana. Yeah, I'll be here all week. Tip your waitress. All right. So I'll just give you guys a couple more minutes to see what you come up with. Um, what do you think? There's another way. I usually put a minus right there, but you'll see why, I think. Okay. So the trick, like before, is to multiply by a disguised form of 1. What's the disguised form of 1 that we need in this case?
Cosecant of x minus cotangent of x.
Okay. So like before, maybe by analogy, we think, well, I definitely need cosecants and cotangents in the same way that in the previous one I needed secants and tangents. Okay, but then the one other wrinkle, just to keep us on our toes, is a minus right there instead of a plus. Okay, now why do we need the minus there? Well, okay, sorry, we could have also done cotangent minus cosecant, right? Saying that would have worked also. But we need the two terms there to have opposite signs because if I multiply all this out, what do I get? Sorry. Okay, what's our u-substitution likely going to be? Yeah. Okay, so if I make it the denominator like before, what's the derivative? What's the derivative of cosecant? Negative, yeah, okay. Negative cosecant cotangent x. And then what's the derivative of cotangent? Careful. Right, it's negative cosecant squared, but there's already a negative, so this will flip plus, like so. Okay, that's why we wanted the minus sign there, because these two things have opposite sign. Okay, so now look what we've got here. What is u? U is exactly the denominator. What's du? Exactly the numerator. And I need a dx right there. So this is again just du over u. Okay. The minus was the critical piece here, because if we didn't put the minus there, then we would have had a plus right there, a plus right here, and then we would have had a minus right there. Okay. Yeah. So sort of by analogy. All right. Now Coy's making a suggestion where multiply by sine divided by sine instead. And then if we did that, that would give us well, cosecant is 1 over sine, so that would be like sine divided by sine squared. And then maybe you could do like a Pythagorean identity or something like that to mess with that. So Coy, why don't you work that one out and see how it turns out, or see if you get stuck, and then maybe we can start with that first thing on Wednesday just for giggles. Okay, so it's 9:54, 9:55. Yeah, so the sheet where I've got picked these problems off of, and there were a couple that I skipped just for the sake of time. Post that basically every day to Canvas, the blank one, and then you guys can have peeks at it. And so yeah, so we'll continue on Wednesday with probably integration by parts. Okay, so I'll kill the stream right here and see you guys whenever.